Okay, so in previous class, actually we already showed you how to use the integral method to derive a particular form of first order, second order, and zero order of rate equation. And next, we are going to show you how to get the rate constants from the irreversible parallel and series reaction. And we also want to introduce the reversible first order reactions. So how to reconstruct the rate equation for this reversible process. So for a just a quick review, for a parallel reactions, so how can we know the one we have or we deal with belongs to parallel reactions? As I mentioned before, you can measure the consumption rate of reactants at different temperature or the rate constant to then you plot the log R versus 1 over T, or you plot the log K versus 1 over T. As long as the data point shows like not a straight line, just a curved line, that implying that, and the curved lines look like this. And after you analyze analyze the data point you recorded from your experiments, you find the consumption rate of reactants is more close to the reaction 1 or the fast reaction. And at the high temperature, and the same thing happens at a total low temperature, which means the consumption rate of reactants is more close to the fast reaction, which is a reaction 2 here. So always the fast path dominate. In this case, we will say the relationship between the reaction 1 and reaction 2 belongs to parallel reactions. And this is one kind of parallel reactions, is we have the same reactants and the same products, and just with different paths. The other type of parallel reactions can be A generate R, or A also can generate product P or Q, okay? That one also belongs to parallel reactions. But in this type of parallel reactions, how to measure the K1 rate constant in reaction 1 and the rate constant in reaction 2 experimentally? So that's what we want to introduce to you, and the technical trick we are going to use also belongs to integral method. So now we are going to show you is what we call an irreversible parallel reaction. So it's a parallel reaction and it's irreversible. So what we have here is we assume the reactant A can generate product R with rate constant K1. And reactant A also can generate product S with reaction 2, and all these reactions belong to first order elementary reactions. So how to design an experiment to measure the rate constant K1 and K2, and further reconstruct the rate equation for each reactions. So now, based on these equations, we can write down the consumption rate of reactant A equals to minus dCA over dt, right? The concentration change of the reactants, change rate of a reactant A, and can be write down like K1 Ca plus K2 Ca, right? Okay, then you can put the Ca together and you got a K1 plus K2 times Ca. Oh, before we move forward, I forgot to mention one thing, important thing. In order to get the two unknown parameter K1 and K2, you also need two equations. So I'm going to show you how to formulate the two equations from your experimental data. Then you can get the K1 and K2 individually. So now we have the first equation, right? And the second equation would be what? Would be yes, you can measure the consumption rate of reactant A, and you also can measure the generation rate of product R and S. So RR equals to K1Ca and RS equals to K2Ca, because we already assume they are first order elementary reactions. So based on these results, I just divided this by this. RR divided by RS. So what I have here is dCr divided by dCs and K1 over K2. So now I have two equations and two unknown parameters. So let's try to use the integral method to get the rate equation individually. So this one I will focus on this. So we can move the Ca to the left-handed side, dt to right-handed side, and take the integral for both sides. And regarding to dt, so integral from 0 to t, and the Ca will be integral from Ca0 to Ca. So you will get these results. Okay? So you use the integral method. Okay, and the second one will be these results, right? We will focus on this part. So what's the dCr? Is the change in concentration of reactant R or product R, right? And the change in the change of the concentration in product S. So you also can be rewrite as Cr minus Cr0 is the change is dCr, right? And Cs minus Cs0. So will be equals to K1 over K2. So now we have two equations. So we try to input our data and to get the value of K1 and K2. So what I'm going to do here is I try to plot the minus log Ca over Ca0 as a y-axis, and I'm going to put a t as a x-axis. Okay, and here I'm going to plot a Cr and Cr as a y-axis and Cs as a x-axis. So next, based on this equation, we know the slope belongs to K1 plus K2, and this one also, the slope will be equals to K1 minus or divided by K2. So as long as I have this data point and after fitting, then I can get the K1 plus K2 equals to certain value and K1 divided by K2 equals to certain value. Then I can get K1 and K2 individually. Okay, so let's do this one. So when this experiment starts, and after time t1, I measure the concentration reactant Ca and also measure the Cr and Cs. Then I can get this data point. And after T2, I can measure the Ca, Cr, and Cs and have this data point. In order to get correct curve or data point, so I will try to record it on T3. So T3, I will measure the Ca, Cr, and Cs as well. So as long as I have 3 or more data points after fitting, you can get the slope. And also know K1 plus K2 equals to specific slope, value of slope. And after fitting, you also know the slope here. So based on these equations, you can get the K1 and K2. Okay? So in some trick can improve the accuracy of the value K1 and K2 is you can try to measure more data points. You can measure the concentration of reactants and products at T4, T5, and T6. If you have more data points after fitting, you can get more accurate slope, and that will help you to get the more correct reaction rate K1 and K2. Okay, so as long as you got the K1 and K2, you can put it back and try to reformulate the rate equation for this equation 1 and equation 2. For example, like minus RA, and there will be minus RA will be K1 times, because first order is CA to 1. And you can directly substitute the value of K1 here. And here will be also my consumption rate of reactant A equals to what? K2 CA2 or CA to 1. K2 you can substitute with the value you just derive or calculate. So this is irreversible parallel reactions. So based on this experimental data and the design, you can reconstruct the rate equation for these parallel reactions. And next slide, I'm going to show you the other examples will be the homogeneous catalyzed reaction. Homogeneous means the phase reaction only involve one phase, right? And the catalyzed reaction means I added some catalyst to lower the activation energy, okay, which can speed up the reaction rate. So in this case, I assume these two reactions happen. Reaction 1 is the A generate product R with K1, rate constant K1, and the other one is when I added the catalyst C, then I have I remodify the chemical equation as A react with catalyst and generate product R, and also have a catalyst, because as you know, catalyst is not consumed during process reactions, and the rate constant here is K2. So the purpose here is also want to know the K1 and K2 desired experiments to measure the K1 and K2. So here, consumption rate of reactant A in reaction 1 can be written down as K1CA. So here, please help me to make an assumption here is we assume it's a first order reaction. And reaction 2, the consumption rate of reactant A can be written down as K2CACC. And this, based on this, we assume it's a second order reaction. Okay, so the total consumption rate of reactant A, you need to sum reaction 1 and reaction 2 together and take the CA outside. So we got the K1 plus K2 CC. CC is the concentration of the catalyst. And next, I'm going to move the CA to the left-handed side, DT to the right-handed side, and take the integral on both sides. So you are going to get the minus log CA divided by CA0, and K1 plus K2 CC times T. This is after integral method, you can get these solutions. And as you know, some people want to convert this expression in terms of the fractional conversion. So CA divided by CA0 equals to 1 minus fractional conversion XA. Okay, so now based on this, if I try to use this as a y-axis and T as a horizontal axis, then the slope will be identical with T up K up of slope, included K1 plus K2 times concentration of catalyst. But purpose here is I want to know the K1 and K2. So idea would be, how about if I don't add the catalyst and I measure the CA at a different time point. So that will be probably I will measure three or four time point. To get after fitting, I got this slope. This slope is the K1. Now I know the K1 and CC at 0, so it's also the K observed and versus CC, so it's a data point here. When I try to add a tiny amount of CC, then I can and also measure the CA at a different time point, 3 or 4 data point. I can get after fitting, I have a slope here, so I can have then I can have this data point. Then I try to end it more CC. I can get this blue curve, blue straight line, and after fitting, I can get a slope here and get this data point. So after fitting, this slope actually is a K2 because you use this as a Y and this is the X. So this is the slope. So some people probably, yes, after class, some people come to me ask about, professor, as long as I get this slope, I know the K1 and I get a slope, and I also know the catalyst which I ended into this reactor so that I can get a K2. Why should I perform extra experiments? Yes, you can, in this case, you can get the K2, but the K2 is not as accurate, as correct as, it's not correct, accurate. It's not correct because, as you know, doing your measurement, always generate some errors. So in order to minimize the error doing measurement, so usually people will do extra to get the extra data point to minimize the errors doing measurements. So if you want to lower the errors doing measurement, you can, and you also can edit the other concentration of CC to generate the fourth or fifth data point. Then after fitting, you can get the more accurate reaction rate constant. Okay, so this is an experimental point of view. You need to repeat to minimize the error generated from doing the measurements. You need to pay attention, like the data you need to measure several times, and also it should be repeatable, something like that. So, or you need to generate more data. So after fitting, you can minimize the standard deviation error part. Okay. So we finished the parallel reactions, but we still have a series reaction, right? So when you measure the consumption rate of reactants or products as a function at different temperature, and you plot log R or log K versus 1/T, and the slope, the curve you have is turned like this. And after fitting with reaction 1 and reaction 2, and you find that your experimental results actually is more close, more fitted with the reactions with the slower reactions. At high temperature regime would be the reaction 2, and at low temperature regime would be reaction 1. So in this case, slow path dominate, it belongs to series reaction. So series reaction means your reactants will generate intermediate substance and finally generate your products. So how to decouple or how to reconstruct the rate constant K1 and K2 from your experimental data? So I will formulate this one. A generate R with rate constant K1 and generate product S with rate constant K2. And doing the experiments, you need to monitor the concentration change as a function of time. And the CA turn like exponential decay, and the CR will increase and reach maxima and decrease, and the CS is all the way increase. So now you have experimental data like this because you always measure the concentration of reactants, intermediate substance, and the products. Okay, so now how to get a K1 and K2? So I will say, first of all, I want to write down the consumption rate of reactant A, generation rate of product R, or intermediate substance R, and generation rate of product S. So consumption rate of reactant A, and we also assume can equals K1Ca. Actually, we assume it belongs to first order reaction. And the RR is K1 is increased and K2 is decreased. The concentration of intermediate substance R. So K1Ca minus K2Cr. And the RS is easy, right? dCs dt is K2Cr. All belongs to first order elementary reactions. Next, I'm going to use the integral method. So we have initial boundary conditions, and after integral, you can get these results. And the solution of Ca can express like this is Ca0 at time 0, and will be the exponential decay, and decay constant will be minus K1T. And now you know the Ca, right? So take a look. As long as you know the Ca, so you can substitute Ca here, and the parameter you don't know is a Cr. So based on this idea, K1Cr, or C1Ca, sorry, and K2Cr is here. So this is the only you don't know the Cr. So based on this equation, you can get the Cr can express like this because it is totally fitted with this equation, right? Y is Cr and P is K2 and the Q actually is this one. So the solutions for this type of equation can express like this, Cr. And we also have the other boundary condition or initial condition means that the total concentration of A0 equals to Ca plus Cr plus Cs. So now you know the Cr, you also know the Ca. So use the Ca0 minus Cr and Ca, then you can get the Cs. Show like this. The detail can be found on page 18 in lecture note. So as long as you have this data and also you have this data, you also collect all this concentration as a function of time. Then we will focus on the Cr, this curve. When Cr reaches maxima, the dCr over dt equals to 0. So use this relationship. We take the Cr deviate with dt and equals to 0. So you can get the t expressed like this. And bring this t maxima back to substitute t, then you will get the Cr maxima. And you can have these two relationship. And regarding to the T maxima, you can get from your experimental data show here, T maxima, you know the value, just substitute it here. And for this Cr maxima, you also know the specific value for this one, so you can substitute this. So now you have two unknown parameter K1, K2, you have two equations. So I believe you can get the K1 and K2 after calculations. And some people also come to me to ask, Professor, it turns out it's not easy to solve this equation, even though I know this and this. It's not easy to get the K1, K2. Oh, is that possible? I only measure the concentration Cr directly, and I just forgot this curve and this curve. Probably, but I provided you the other information here as the other ways here. Based on if you did measure the Ca as a function of time, then you have chance to know the K1, right? And for these results, as long as you know this T maxima K1 is easy to get the K2. It's the other solution to get the K2. Okay, K1 and K2. And in the other, additionally, in previous slide, lots of people, including me, tell that in serious reaction, always slower reaction dominate the whole reaction rate. People always say this. So do you have evidence? So I'm going to base on these results and show you some evidence to convince you. in series reaction, always slower reaction dominate the reaction rate. So in this series reaction, we assume K2 is much larger than K1, means this is faster, this is slower. So when I focus on the generation rate of product, its K2 is much larger, so exponential minus is quite large term, so you can directly ignore this value, right? And K2 is much larger than K1, so you can delete this one. So you got a 1 minus this minus exponential to minus K1t, show like this. So you can know the generation, the concentration of product S is dominated or controlled by the K1, which is a slower reaction one. So slow reaction dominate the concentration of product. The same idea if K1 is much larger than K2, which means this is a slower reaction. So I just K2, I just put substitute this information inside these solutions. And K2 is quite small, and K1 is quite large, so I can directly delete this term. And also K1 is quite large, and this is deleted. So K1 minus K1, so you get the minus exponential to minus K2t. So K2 is lower one, right? So generate concentration of product is dominate controlled by the slower reaction with rate constant K2. So this is always slower reaction dominate the generation of the product. So this is also just the summary for this case. I just put everything information here together. Okay, the same content. In previous slide, page 43 and 44, I just separate them into two slides, and hope you can easier to have some idea about these questions. Okay, so let's move to the last examples here. Here we are going to talk about the reversible reactions with the first order. It's a first order reversible reactions. So far we haven't have chance to discuss about the reversible process, right? In previous examples or previous questions, actually the case we show you belongs to irreversible reactions. Okay, so this is the only one we talk about the reversible process. And due to it is a first order reactions, so when I try to formulate the chemical equation, like I have product A and generate, I have reactant A and generate product R. The forward rate constant is K1 and backward constant is K2. And because it is reversible reactions, so it means when these reactions reach equilibrium conditions, and equilibrium condition actually means the concentration of reactants and products does not change with time. Under that kind of situations, the rate constant Kc, or we call it as the equilibrium constant, equals to K1 divided by K2. And the other information I want to show you is Ca0 means the initial concentration of reactant A, minus Ca is the remaining concentration of reactant A, is equals to what? Equals to the reacted portion. So its reacted portion will be equals to Cr minus Cr0 will be equals to produced portion, because when you consume 1 mole of A, you will generate 1 mole of product R. So reacted portion will equals to produced portion. This is the other information. And additionally, we want to highlight the initial concentration of the reactants and products. So Cr0 divided by Ca0 equals to M. M actually is the constants can be 1, 2, 3 depending on the initial concentration ratio between the product divided by the reactants. And XAE means the fractional conversion of reactant A under the equilibrium condition equals to 1 minus CAE divided by CA0. So still put E here, means that fractional conversion of reactant A under the equilibrium condition can express like this. Okay, so in order to formulate the rate equation for this first order reversible reactions, so we start from the dCr over dT is a generation rate of product R equals to minus dCA over dt equals to consumption rate of reactant A. And in the meantime, it can also be written down as KCA minus KCR, KCA minus KCR, and this from this is due to, as you know, Ca remaining concentration of reactant A equals to the initial concentration of reactant A minus what? Fractional conversion of reactant A times Ca0, means how much A be converted to product. So you have initial and you minus the converted part, it will be equal to remaining part. So you take the deviated for this equations, so you got and put a minus deviated, so put a it turns out the minus dCA, and this is constant, so minus positive, CA0 is constant, so you put here and dXA. So you directly substitute minus dCA here as a CA0 dXA, so you got this relationship. So far we have it here, right? Okay, so next, don't forget, just a quick reminder, the rate equation I'm going to derive will be in terms of XA and dt. So that's why we want to convert the dCA into dXA. And this part we only want to link or express this in terms of XA. So here Ca will be equals to Ca0 minus Ca0XA will be the same with this one. And minus K2 CR, what's the CR? CR should be CR0 plus the produced portion, right? CR0 will be equals to MCA0 plus the converted A, so be you minus this term, so it will be plus the produced portion will be shown here. So now I have these equations, and in terms of XA and also dt. Okay, it turns good, right? But here, if you look carefully, Ca0 is the concentration of reactant A. You know that, you all know this, and this. But there are two parameters you haven't have any idea is K1 and K2. In order to get the solutions for these equations, we need to know what's the K1 and K2 here. So there's the other clue, the other information we know here is a reversible reactions. So when this reaction reach equilibrium conditions, we know the concentration of reactants does not change with time at CAE equals to 0. And when it reaches equilibrium means this product, how much it converted to product will be how much it converted back to reactants. So K1 CAE will be equals to K2 CRE. So I highlight the E, it means that I want to highlight is at equilibrium conditions. So now what kind of information I have here is the purpose that I want to know the relationship between K1 and K2. So here, equilibrium constant equals to K1 divided by K2, right? And based on this equation, K1 divided by K2 will be moved to right-hand side, will be CRE divided by CAE. put here. Okay? But we still don't know the relationship between K1 and K2 even though we write this down, right? So back to here, when it reaches equilibrium conditions, dCA, the concentration of reactant A remain constant. So under this situation, dxAt over dx will be equals to 0. So this will be 0. So these equations for sure be equals to 0. So I can know K1 divided by K2 would be equals to this term divided by this term. So when so it will, and you can delete CA0 together, so you got a 1 minus XA. 1 minus XA, don't forget put the E here, and M plus XA, E. Okay, so we got this relationship. So based on this, we know K2 can express in terms of K1, show like this. And we put this information back to substitute K2 in terms of K1. So rewrite this equation will be show like this. And next we are going to get a solution, right? So we are going to use an integral method to remove the parameter XA back to left-handed side dt to right-handed side and take the integral for both sides. For t starting from 0 to t and xa is from fractional conversion. Before reaction happens will be equals to 0, so it's 0 to xa. Okay? So you will get this result. Okay, any questions? Oh, so now you already get the results, right? So next, if I try to use this as a y-axis, this as an x-axis, and if I input the xa at different time point and the line or the data shows it is a straight line, which implies that this equations belongs to first order reversible reactions. Okay, the m is no parameters. You know what's m because you can measure the initial concentration of reactants and also the product. Okay, so next I just copy the results and try to show you when I try to use this as a y and this a t as a x. So as long as the slope you get is a straight slope, then based on the slope you also can know, and this one you know, right? So based on the slope you can know what's the rate constant. Okay, and for sure regarding to the XAE, as long as you from your experiments you have chance to know the XAE, right? Because when you always measure the concentration, consumption rate of reactant A or generation rate of product R, then you can, when you find the concentration does not change with time under that situation, you can know what's the XAE. So this is also based on your experimental observation, and this is depending on how much you ended, you can measure that, right? Because you know the initial concentration of reactants and products. So based on this data, you can further get what's the K1. As long as you get the K1, and you can get the K2. And you also can reconstruct the rate equation here. Okay? And the other information is probably you will ask, you're familiar with these reactions, right? Because in previous slide we did learn first order irreversible reactions, and here is a reversible reactions. So sometimes when you check the solutions, you look, they are from you are familiar with these solutions. Yes. if you check the one you learned for the irreversible first order reactions on page about 29 in PPT slide, the solutions show like this. If you compare these solutions with these reactions, so you will find when XA is so irreversible first order, what this means? Irreversible means, if you back to irreversible means the fractional conversion of reactant A on equilibrium will be equals to 1, right? Because it's all the way to the product, the reaction all the way to the product. So in this case, XAE should be equals to 1. So your left-handed side will be the same, right? And when we consider right-handed side here, XAE equals to 1. So here you only have K1T. K1 actually is identical. It's the same with K. So in this, you compare these results, you know that irreversible, the solutions of irreversible first order reactions is just the special case in these solutions, while XAE equals to 1. Okay? And this I also highlight while XAE equals to 1, CAE equals to 0, because irreversible reactions means the reaction all the way to generate product. So when it reaches equilibrium condition means we only have we don't have reactants anymore. We only have product. Okay. So I'm going to give you a summary here. So in this section 2, we show you how to analyze your data by your experimental data to reconstruct the rate equation. So if you don't have any idea what's the reaction order of your interesting chemical reactions, I would suggest you to use the half or fractional lifetime analyze, and that can be your first trial to determine the reaction order. And by plotting the log T half lifetime or fractional lifetime versus log CA0, based on after fitting, you can get the reaction order from the slope. But just a quick reminder, this method, before you use that equation or that results, you need to pay attention that the reaction order cannot be 1. Under that situation, you can use that the solutions we derived in previous slide. And this is a differential method. And the other method we call it an integral method. And in that method, we show you how to derive the particular form for first, second, and zero order rate equation. And as long as you got these particular forms and you input the Ca concentration reactants at as a function of time, then you can check whether your interesting reactions belongs to first, second, or zero order reactions, or none of them. Okay, so the integral method can only deal with these three orders of rate equation. And the third part is when we mentioned that while your reactions involve two elementary reactions, and based on you plot the log R versus 1 over T or log K versus 1 over T, if it is a curved line like this or this, then you can determine your two elementary reactions. Your reactions involve two elementary reactions, and the relationship probably will belong to parallel or serial reactions, and you have chance to reconstruct these equations, right? These rate equations by determining the K1 rate constant, K1 and K2. And regarding to the equilibrium conditions for reversible reactions, The last one we just show you, irreversible rate equation can be reduced from reversible rate equation. Is a special case, right, for reversible rate equation. Okay, so